This right here is an acoustic levitator. And basically what it's able to do is it can levitate small objects in between both of these ultrasonic transducers. And we have another video that goes over in more depth about what ultrasonic sensors are and how they work in different contexts. But basically, both of these transducers are like the transmitters on the ultrasonic sensors, and they both release ultrasonic waves through a different process that we're going to go over pretty soon. And because of those two waves, when they combine, they're able to levitate a small object in between both of these transducers. So I'm not going to show a demonstration because I got this actually in the mail like a couple of weeks back and it was broken and it wasn't working. So if you want a demonstration, there's other videos online that show that pretty well. But in this video, we actually go over a pretty good explanation of how this entire system works. So basically, you can see that there's like a full board here. What does the board do? Well, when we actually have like, let's just say an input of around 5 to 12 volts, that's like the approximate input. We take that in and then we have something known as a crystal oscillator. And what a crystal oscillator is that it's like a type of circuit that changes our DC voltage into like a repeating voltage pattern. So we have the input and it turns on and off, high and low. It keeps going back and forth, and that creates our AC signal. And now that we have an AC signal, we take that signal and we can either amplify it, some circuits amplify it, or it can actually go to, and it can hit the piezoelectric crystal inside of these ultrasonic transducers. And when it hits the piezoelectric crystal, we know how piezoelectric crystals work. That creates an ultrasonic wave. And so that happens in both of these transducers right here. It creates the ultrasonic wave, and that's how the rest of the system works. And keep in mind that when we create the wave, we need it to be like the exact same type of wave, like the same frequency, same wavelength, same everything. So we have to have a specific type of signal created by the crystal oscillator for it to actually happen. So now we're going to dive into way more depth. So welcome back to Knowledge on Ears, and let's get going. So now that we have explored what acoustic levitation is and how these ultrasonic transducers are able to generate ultrasonic waves, we have to understand how these ultrasonic waves are able to actually levitate these small objects in the air. And to understand that, we have to first look at the fundamental types of waves. So there's transverse waves and there's longitudinal waves. And basically, when you imagine what a wave is in your head, you probably imagine transverse waves, which are like the basic motion of a wave. And what transverse waves are is basically when the particles move up and down while the entire wave is moving in one direction. So the textbook definition would be like a wave where the direction, where the movement of the particles is perpendicular to the movement of the wave. And so light waves are a type of transverse wave. But on the other hand, sound waves are not transverse. Those are longitudinal. And ultrasonic waves are longitudinal because they're a type of sound wave, obviously. So longitudinal waves are where the particles are moving back and forth while the entire wave is moving forward. So basically, these back and forth movements of the particles is creating areas of compression and areas of rarefaction. Sorry, it's hard to pronounce, but basically, these two different areas is what allows our ultrasonic waves to actually levitate particles, and we're going to get into that soon. But basically, there's just different areas created, so more pressure and less pressure in different areas. Now let's get into how these two different longitudinal waves can be used to levitate a small object. So right here we have an enlarged image of this same ultrasonic transducer system. So it's just enlarged. We have two ultrasonic transducers and they're each transmitting a wave. So this one has a purple wave being sent out in this direction, and this one has an orange ultrasonic wave being sent out in this direction. Just to clarify, you don't always need two transducers. You can also have a reflector sometimes, and this reflector will reflect the wave being sent out by one transducer at the exact right timing to create the same example and levitate a small object. So you don't always need two transducers, but obviously having two transducers makes the levitation much stronger. Also, one more very important thing to prevent any confusion. In the past, I just talked about how ultrasonic waves are longitudinal waves, not transverse, but I just drew them as transverse waves. Keep in mind, I am not showing that these are transverse waves. These are still longitudinal waves, but it's just easier to draw them as transverse waves. Basically, they are representing different things. Normally, transverse waves, the points represent how the particles are moving up and down. In this case, the top point I am representing as having compression, and the bottom point is representing the rarefaction, okay? And the direction of movement is representing the direction the wave is moving. So keep that in mind. Now, how are we able to levitate objects? Basically, when you have two of the exact same wave, exact same frequency, exact same everything, and you send them at the right time, you can create a standing wave, which is like this. And basically, the cool thing about a standing wave is that you are creating alternating regions of having the wave squished together and stretched out. So there's alternating regions of that, and there's also regions of no movement at all. These are called the antinodes and the nodes. And I'm going to try my best to explain standing waves because they're pretty hard to explain. So basically, antinodes are these areas. So these type of areas right here. And that is when the two waves are kind of, you can see that they're opposite. That's representing how there's a lot of compression and a lot of rarefacting. So it's kind of moving in and out like that. And a lot of different people represent, like there's other videos that represent standing waves as like a slinky that you push and pull. That's pretty smart because it shows how it's having rarefacting and compression. But on the other hand, there's also nodes. These are the opposite. This is where there's very little movement. And so no matter how the rest of the wave is moving, you can see that this is not going to move. So these waves don't move at all. So those are the antinodes and the nodes. But where do you think, if you have a particle, where do you think the particle will go? Like if you have a small object and you're putting it inside these two ultrasonic transducers to levitate it, where will it go? Well, basically, it really depends on the size of the particle. Bigger particles, basically, when they're big, the forces that push it, like the compression and the refracting forces, they push it away from the antinodes and they push it into the node, right? So that's why bigger particles, when you put them into the levitator, will go into the node area. Obviously, if they're too big, they just won't be levitated at all, but a little bit bigger, they will go into the node areas. But small particles that can be easily pushed around by the rarefacting and the compression forces, those go into the antinodes, like right here, because they get pushed in together using these compression and rarefacting forces. They get pushed and pulled, and at some point they settle into the antinode areas like that. So basically, it depends on the size of your particle, and you might have to test that out. So I hope this makes sense. It's a little bit complicated, but I tried my best to explain it. Thank you for listening. Bye!